Okay, so today we have the last topic in our discussion of Laplace transforms. This is Dirac delta and impulse response. So, first of all, I'm going to have to tell you some notion of what the Dirac delta is, right? Unfortunately, to make it rigorous, to make it mathematically strict, you need very high level mathematics that we're not going to get into in this class. So why am I bringing it up? The reason why is because this is important for applications. The Dirac delta comes up a lot in physics and related fields. So the original motivation of it was the following. Imagine a function ds, which is, or actually, for some reason I'm calling it both ds and rs in my notes. Well, let's just pick one. ds. This is going to be 0 if t is less than s, or negative s, or greater than s, and it's going to be 1 over 2s if negative t less than or equal to s less than or equal to t. So this is ds of t. And s is not related to t. S is just a constant. Okay? So this is a perfectly valid function that you can think about, right? Its graph looks like if negative s is right here and positive s is right here. The graph looks like something like this, right? So we can think of it as a kind of rectangular wave. Okay? So let's notice the integral from negative infinity to positive infinity of ds with respect to t. Well, first of all, it's 0 everywhere that's not between negative s and s, so we can just rewrite this as the integral from negative s to s of ds. ds is actually just going to be 1 over 2s. 1 over 2s dt. You do this integral, you get t divided by 2s, evaluated from t equals negative s up to t equals positive s. And 1, 2, 3, that's 1. Okay? So, for every value of s, these functions, there's one function for each value of s, where s is a constant again. For each value of s, though, you get one of these square waves, and the integral from negative infinity to positive infinity is 1. Okay? So the Dirac delta is a limit delta of t equals limit as s approaches 0 ds of t. Now that might not make a lot of sense to you, and if so, you're in good company, because it doesn't make sense. There's a lot of questions here that are all going to come up along the lines of, hey, can you actually do that? And the answer is no, you cannot actually do that. This is not a function. However, it is a symbol that we can do math on. That's all we need to know for this class. The important thing about this weird object is that it is a symbol that we can do math on. So the way that we're going to define it is like this. Definition. The Dirac delta is a symbol delta of t such that for any non-negative real value, which we could call A, and any continuous function which we could call f of t, the integral from 0 to infinity of f of t times delta of t minus a is just going to be f of a. This is called the sifting property of the Dirac delta. By the way, some people call this the Dirac delta function, which is a very bad term for it, because, as I said, it's not a function. It's a thing. So, therefore, I'm not going to call this the Dirac delta function, even though you might hear it being called the Dirac delta function or the delta function in your engineering class. The reason why is because, like I said, it's not a function. And even your engineering professor will agree with that. They'll say something along the lines of, the Dirac delta function is not a function, which, in that case, you should come up with a different name for it. So I'm just going to call it the Dirac delta. Okay. In particular, we can discuss the Laplace transform of a Dirac delta. So if you have delta of t minus a, by definition, this is the integral from 0 to infinity of e to the negative st times delta of t minus a. And then that is just, well, according to this property right here, it's going to have to be e to the negative as. And that puts rule 9 on our table. F of t equals delta of t minus a. The Laplace transform is e to the negative as. Okay. In particular, if a is 0, then this becomes e to the 0, which is 1. So the Laplace transform of delta of t is just 1. Okay? And if you think about that for a second, you realize that there's no function that has that property, which is fine, because the Dirac delta is not a function. Okay? So, what is this thing supposed to mean? Well, like I said, it's supposed to be interpreted as a limit of these square waves that have area 1. So it can be used to model things that happen almost instantaneously. Like, for example, a sudden voltage spike in a circuit, or the force of a bat hitting a baseball. These things can be modeled using a Dirac delta. Okay? So, therefore, we can work with initial value problems that involve the Dirac delta as the inhomogeneous term. So, let's look at some examples. Okay, let's suppose we have the following initial value problem. Y prime prime plus 4y equals delta of t with the initial condition y of 0 equals 0 and y prime of 0 equals 0. Okay. Now, when you have a Dirac delta in your inhomogeneous term, you always have to use Laplace transforms. There's simply no other way to make sense of this thing. Okay? So, we're going to take the Laplace transform of both sides. Y prime prime plus 4y equals Laplace transform of delta of t. This is the Laplace transform of y prime prime plus 4 times the Laplace transform of y equals Laplace transform of delta of t. Okay, Laplace transform of y prime prime, as we saw in the last lecture, that's going to be s squared times the Laplace transform of y minus 0 times s minus 0. Then add to this 4 times the Laplace transform of y. This equals the Laplace transform of delta of t. The Laplace transform of delta of t is e to the negative as. In this case, a is 0. So that's just going to be e to the 0, which is 1. So, this comes out to be 1 on the right-hand side there. Okay, so now we have an equation that we can solve for capital Y, the Laplace transform of our solution. We get here s squared plus 4 times capital Y equals 1, in which case capital Y equals 1 over s squared plus 4. And then we have to take the inverse Laplace transform of that. Well, that looks an awful lot like k over s squared plus k squared, where k is equal to 2. The only trouble is we don't have a 2 in the numerator, But that's fine. We can just multiply by 1/2 and 2 simultaneously. And now we're starting to get something that looks like the Laplace transform of the sine of 2t. So y of t, the solution, is 1/2 sine of 2t. And that's our answer. Okay. So for today's lecture, it's going to be more of the same. It's going to be more of using Laplace transform methods to solve initial value problems. It's just now there's this weird delta thing that keeps cropping up. That's it. Okay. So we'll do some more examples. Let's suppose we have y prime prime plus 2y prime plus y. This is equal to t plus delta of t. With the initial conditions y of 0 equals 0, y prime of 0 equals 1. Okay, once again, the fact that we have a delta in here anywhere means that we have to use Laplace transform methods. So we're going to take the Laplace transform of both sides. So y prime prime plus 2y prime plus y equals Laplace transform of t plus delta of t. This turns into, by the linearity of the Laplace transform, this turns into Laplace transform of y prime prime plus 2 Laplace transform of y prime plus Laplace transform of y equals Laplace transform of t plus Laplace transform of delta of t. Okay. So then the Laplace transform of y prime prime is going to be s squared times the Laplace transform of y minus 0 times s minus 1 plus 2 times the Laplace transform of y prime is going to be s times the Laplace transform of y minus y of 0. Then add to this Laplace transform of y equals Laplace transform of t, which is 1 over s squared, if you just look at the table. And Laplace transform of delta of t is 1. Okay? So we can keep going. We get s squared y plus 2sy plus y minus 1 equals 1 over s squared plus 1. This gives us s squared plus 2s plus 1 times y equals 1 over s squared plus 2. Now, s squared plus 2s plus 1 can be factored into s plus 1 squared, and then we can move that over to the right-hand side, so we get y equals, yes, but first I'd like to find a common denominator between these two things. So this is s plus 1 squared times y equals 2s squared over s squared plus 1 over s squared is 2s squared plus 1 divided by s squared. Divide, and you get y equals 2s squared plus 1 divided by s squared times s plus 1 squared. And now what we need to do is find the inverse Laplace transform of that. So, once again, we're going to have to use partial fraction decomposition. So we have 2s squared plus 1 divided by s squared times s plus 1 squared. This decomposes into a over s plus b over s squared plus c over s plus 1 plus d over s plus 1 squared. You can multiply through. You'll get 2s squared plus 1 equals a times s plus 1 squared plus b times s plus 1 squared plus c times s squared times s plus 1 plus d times s squared. This is 2s squared plus 1 equals a times s cubed plus 2s squared plus s plus b times s squared plus 2s plus 1 plus c times s cubed plus s squared plus d times s squared. And we collect like powers, or we collect like terms in powers of s as we always do. So 2s squared plus 1 equals, let's see here, a plus c times s cubed plus 2a plus b plus c plus d times s squared plus a plus 2b times s plus b times s to the 0. Alright, so this gives us a system of equations that we can solve for a, b, c, and d. A plus c equals 0. 2a plus b plus c plus d equals 2. A plus 2b equals 0. And b equals 1. Okay, that's not impossible to solve. B is 1, so therefore the second equation becomes a plus 2 equals 0. In other words, a equals negative 2. If a is negative 2, then the first equation becomes negative 2 plus c equals 0, which makes it pretty clear that c has to be 2. And then the second equation, based on everything that we have so far, becomes, let's see here, negative 4 plus 1 plus 2 plus d equals 2. And that means that d has to be negative 3. Okay. So altogether, this thing turns into, let's see here, a, so negative 2 divided by s, plus b, so 1 over s squared, plus 2 over s plus 1, and then minus 3 over s plus 1 squared. Okay, now I'm going to erase the part where we do the partial fractions because we no longer need those computations. So if you need to look at that for a second, pause the video. Right, so we need to find the inverse Laplace transform of this thing. Okay. Well, we can start with inverse Laplace transform of negative 2 over s is just negative 2. Inverse Laplace transform of 1 over s squared is just t. Inverse Laplace transform of 2 over s plus 1 is 2e to the negative t. And then the inverse Laplace transform of 3 over s plus 1 squared. That's a little bit harder. What we're dealing with is something like in Rule 8, where we have a function that we know about, but it's shifted by some value a. So in order to deal with this, I'm going to name a new function. So this is going to be minus 3 times something, right? But that something is what we're trying to figure out. I'm going to name g of s plus 1 equal to 1 over s plus 1 squared. Okay, well in that case, g of s is going to have to be just 1 over s squared. We know the inverse Laplace transform of that. That is just t. Okay? So, now we apply Rule 8 of this table. We're going to get e to the negative 1 t times g of t, which is t. So t e to the negative 1 t. And that is our solution. Let's do one more example, because ultimately this just comes down to learning one more rule for your Laplace transform table, right? Involving these delta of t minus a. So, y prime prime plus 4y prime plus 4y. I'm going to say this is equal to 1 plus delta of t minus 2. With the initial conditions y of 0 equals 0 and y prime of 0 equals 0. Okay. So, because there's a delta in here, we're going to have to take the Laplace transform of both sides. So Laplace transform of y prime prime plus 4 Laplace transform of y prime plus 4 Laplace transform of y equals Laplace transform of 1 plus Laplace transform of delta of t minus 2. Laplace transform of y prime prime in this case is just going to be s squared times the Laplace transform of y, then minus 0, plus 4. Laplace transform of y prime is sy minus 0, then plus 4 capital Y equals Laplace transform of 1 is 1 over s, and Laplace transform of delta of t minus 2 is e to the negative 2s, if I'm not mistaken. Yes. Okay. So then this becomes s plus 2 squared times y equals 1 over s plus e to the negative 2s. And then in that case, y is equal to 1 over s times s plus 2 squared plus e to the negative 2s times 1 over s plus 2 squared. This one we'll do by partial fractions. This one is going to involve rule 7 from the table because it has an exponential. And it's also going to involve rule 8 because it's a shifting of a function that we know, 1 over s squared. So let's get down to business on finding the inverse Laplace transform. We'll start with the easier part, which is doing partial fractions on this thing. So 1 over s times s plus 2 squared is a over s plus b over s plus 2 plus c over s plus 2 squared. Multiply through. You get 1 equals a times s plus 2 squared plus b s times s plus 2 plus c s. This becomes 1 equals a times s squared plus 4s plus 4 plus b times s squared plus 2s plus cs. In that case, 1 equals a plus b times s squared plus 4a plus 2b plus c times s plus 4a times s to the 0. This gives us a system of equations. We have a plus b equals 0, 4a plus 2b plus c equals 0, and then 4a equals 1. In that case, a is going to have to be 1/4, b is going to have to be negative 1/4, that means that this second equation becomes, let's see, 4 times 1/4 is 1, then minus 2 times 1/4 is minus 1/2, plus c equals 0. 1 minus 1/2 is, of course, 1/2, so therefore c equals negative 1/2. Okay, and so that gives us the first term here, capital Y equals 1/4 1 over S minus 1/4 1 over S plus 2 minus 1/2 1 over S plus 2 squared. And then we still have this e to the negative 2s 1 over s plus 2 squared here. So once again, I'm going to erase the partial fraction decomposition. Again, if you need to see that for a few moments, then I suggest you pause the video. Because now what we need to do is handle 1 over s plus 2 squared. So I'm going to define that as g of s plus 2. I'm going to call that 1 over s plus 2 squared. In which case, g of s is just 1 over s squared. And so then lowercase g of t, the inverse Laplace transform, is just going to be t. Now, we have g of s minus negative 2, so this is going to be e to the negative 2t times g of t. So, what we get here is y of t equals 1/4 of 1 minus 1/4 of e to the negative t, e to the negative 2t, sorry, minus 1/2 of, okay, this is going to have to be e to the negative 2t times g of t, which is t. Then add to this something. In order to figure out that something, we're going to have to use rule 7. So this time, because I'm using g for something else, I'm going to call it h of s. H of s is going to be 1 over s plus 2 squared. And we actually already figured out the inverse Laplace transform of that. Lowercase h of t is apparently t e to the negative 2t. So, according to rule 7 of our table, we're going to need u of t minus 2 for this exponential, and then g of t minus 2 for this g. U of t minus 2, h of t minus 2. Also, I said g before, but I meant to say h. And then finally, we already know what h of t is, so this just becomes 1/4 minus 1/4 e to the negative 2t minus 1/2 t e to the negative 2t plus u of t minus 2 times t minus 2 e to the negative 2 t minus 2. And that right there is our solution. Okay? So, not very much different from what the sorts of things that we had to do before, but now we might need to pull in a few more rules that were a little obscure before. In any case, that's all for today. See you in the next one.